The number of physics specialists in secondary schools is at an all-time low. Many LEAs have set up their own CPD schemes to help address this problem and improve the quality of physics teaching at Key Stage 3 and 4. Barnet LEA has brought in Steve Hearn, a head of science and a network coordinator from the Institute of Physics, to help non-specialist physics teachers improve their physics teaching for Key Stage 3.
My name is Jifty Chugg. I'm the secondary strategy consultant for Barnet LEA for science. I deliver the strategy in Barnet to all the 21 secondary schools that we have. I deliver the training, I then go into schools and I work with teachers to implement aspects of that training.
My name is Kelly Fulser and I teach at St. Mary's Church of England High School, and I teach Key Stage 3, 4 and 5 and specializing in chemistry at A level. Do I feel confident in teaching physics? I would have to say no.
What are you feeling?
Steve's approach is to illustrate the nature of electricity using a series of practical demonstrations. These included a torch with no battery to show how electricity can be generated, an energy board to illustrate energy transfers, and how to make a battery from fruit. These experiments are designed to show how ideas in physics link together.
Okay, I'm going to pass these torches out for the guys to have a quick look at. I chose electricity because, again, the whole idea of voltage and current to children at Key Stage 3 are mysterious. It's a very abstract area of physics. The tendency is to treat voltage and current, and indeed electrical power, as just the same thing. They're all electricity. So you won't see any battery in there, but you will see a nice bright red coil. It's claimed that if you shake these torches for 20 seconds, they stay alight, bright enough to read a map for 5 minutes. Would any of you like to guess what's used to store the energy?
Question.
It is. And if you look inside the one that's cut away, you will see a little squished disc-like thing, a special version of the capacitor we've been using.
So, last lesson we were talking about all the different types of circuits that we can have, and our main topic is energy and electricity. So I want you to think about what were the two main different types of circuits that we can have. Yeah?
Parallel and series.
Okay, very good. So
A few weeks later, Kelly incorporates some of Steve's ideas with her Year 9 group. As a starting point, she gets the students to form a human circuit to illustrate current flow.
very good. This is excellent. Okay, I want you to open the switch. What happens? Very good. You guys are superstars. You guys are going to become the experts on a torch without a battery. So you've got two different parts of this. You're going to get a torch, you're going to get crocodile clips, and you're going to get an LED. And I want you guys to generate electricity. Okay?
Their version of the torch does not contain a capacitor. It is simply a coil of wire wrapped around a tube containing a magnet.
And it took them a while to actually realize that they needed to shake it and they needed to make it so that they could generate electricity that way. And you could see that some of them had to think back to, okay, electromagnets. What do you need for an electromagnet? And then you guys can go on as a group to the energy board, and you guys can move up here and use the energy board. Are there any questions at all?
Does this electrocute you?
No, you will be fine. You're cool. But it was great to see them actually like picking it up and sort of looking at it being like, how can I generate electricity?
So I've connected up the shaking torch to the motor, and I'll get Kelly to come out and do some mechanical work, shaking the magnet from side to side through the coil. And we need to look carefully at the motion of the rotor here. So what we see is the rotor sort of jittering from side to side. Doesn't make continuous rotations. Okay? This is because the current keeps changing direction in our circuit. Okay, now,
See, that one went along.
it did. Now let's just add a component. So we'll add a one-way valve called a diode. We have these little diodes inside this torch. We have a capacitor like this inside this torch. Let's just see what effect the diode has on our simple model's behaviour. Okay, it's going one way. Right, Kelly? And we'll just switch the diode around, and now it's turning the other way. So we can learn that the direction of flow of the current determines which way the motor turns. It's actually very hard work, and again, using something like this reinforces this idea that you have to do work to produce power.
Sam, can you tell me what you ended up finding? How did you generate electricity?
By shaking this, and it would create electricity.
Okay, so what did you have to do? What did you connect?
We connected the wires from this to the crocodile clips and
Okay.
the LED bulb.
What's going to happen when you generate electricity?
The bulb will light up.
Okay, perfect. Let's see. And can you generate electricity? Can you get the bulb to stay on for longer? What do you need to do? Can you do it? Shake it what? Okay, give it a go. And then all of a sudden, as soon as you shake it, just like we did in our inset, the teachers, then suddenly you start shaking it and then asking the one student, Sam, okay, shake it even harder and stuff. And you can see that he's getting even more sweaty and stuff. And it was really funny because that's what we did as teachers as well.
Well, once you start to think about teaching energy and to integrate it into your teaching, then it's nice to have a board like the SEP board, which has a lot of bits that you use often, fixed in one place. What you can do is do the very simple experiments that you have to do, very conveniently, with very easy classroom management techniques. But then, with a bit of imagination, you can begin to expand the board and bolt things on. And that's effectively what I was doing with the shaking torch scenario.
Some of the things Steve was bolting on were a capacitor and a voltmeter.
So if I get Dave to do the work this time. So I'm looking to get this up to about 3 volts or so. We're up to 1.2, we're up to 2 volts. So we need to produce a bit more power, Dave.
Shake it.
2.5, another half volt. The extra half volt is the killer. He's getting fatigued now. Okay, I think Dave is entering distress now, so we'll stop at 2.8. We'll stop at 2.8. That's fine. That's good. Now then, thank you, Dave. Now the nice thing is disconnect our voltmeter. The energy is stored in the capacitor, and what I will do finally is connect the capacitor to the LED, light emitting diode on the board, and we'll see it run for a bit. And on comes the LED.
I love the tube with the coil with the magnet in it trying to generate electricity with the light emitting diode there. And thinking about the energy transfer there. Children find that very hard. We get them to work with electromagnets, but they don't really understand what is happening. And they don't understand about generating electricity at all.
We want to see if we can, what's going to happen then? What are we looking at then?
We're looking at the gravitational potential energy
Being transferred to
the buzzer to make sound energy.
Okay, let's see if it works. Okay, can we sort of hear that? Mm-hmm. Okay. Do we want to then try... Oh, there you go. Okay, so there's our buzzer. So what then do we think? What might be wrong? Why isn't it sounding when we're actually dropping it down? Think about the way that electricity flows. Think about what we need to do.
Maybe the string needs to be longer.
The string needs to be longer, you think? I think, so what did you say, Sam?
I think the wires are plugged into the wrong connectors.
Okay, so you think the wires are plugged into the wrong connectors, okay? So do we want to switch the wires around then? The kids, just to see their faces sort of light up when they actually got the transfer of the light energy into the sound, or the light energy into making the fan move and stuff. They found that really, really interesting, and they really liked that. Drop it now. There you go. So good job, okay? So we're together as a team. You guys figured out how you can solve that, okay? So we transferred what kind of energy? We changed gravitational into
Sound.
But did it go right from sound? Or what do we have underneath here? What do we have connected there? We've got, good. So it went from gravitational to
electrical
to
sound.
very good, okay? Excellent. Okay.
Steve went on to add some more surprising components to the energy board. He called them fruit batteries. The idea behind this was to show the basic ingredients of a conventional battery.
I'm just going to stick these 2 zinc electrodes into the tomato. And I'll just see whether I can measure any voltage. And connect it to the zinc. And I'll Well, it's certainly very small. Okay, that's 2 zinc. Let's try 2 coppers. Yeah, it's flicking around and it's about 4 or 5 millivolts. Now I'm going to try a copper and a zinc in the same tomato. And on the scale that I was using, it's gone completely off scale. It's a massive number on that scale. So if I change scale, I'm producing, that's a steady reading of nearly a volt. That's definitely a voltage. So I need to use 2 different sorts of metals, and providing I connect those metals by something acidic, so any sort of fruit like a tomato or a lemon, I can produce a voltage.
So we want to see which is the fruit that gives us the greatest voltage. And you want to think about 2 key things. How are you going to actually measure the voltage? What are you using? And how are you going to make it a fair test?
The fruit batteries, I think, an amazing model to use for children to generate electricity. And they can very quickly see what is it that works well. But they realise that, you know, if they move the electrodes closer, they will get a higher voltage.
It's got a negative.
It's got a negative. What do you think would happen if you changed these around?
It would be positive.
Okay. Why did that? Do you know why that happened?
Because these 2 are switched around.
They're switched around, okay. And what do we know about electricity? Which way do the electrons move?
Move from negative to positive.
Perfect. Okay, so we just had them switched around. So now you've got a positive reading. Okay? Excellent. Really, really good.
How does this relate to series and parallel and to connecting batteries in series and parallel? How would we connect these 2 tomato cells in series? Any ideas?
You need to make sure the electrodes were not the same. You didn't connect the same electrodes to it. In series, yeah, not the same.
So if I connect this zinc to this copper, anybody like to guess what the voltage might be?
Approximately 2 volts, just under 2 volts.
Let's have a look. Close to 2 volts. Yeah, pretty close, 1.8. Similarly, if we were going to go with a parallel connection, zinc to zinc, copper to copper, and then finally measure the voltage, 0.9. I don't think necessarily it's a bad thing that there aren't many physicists teaching at that level. I mean, it would be great if there were more. I think as long as the teachers that are doing the physics teaching at Key Stage 3 are well supported, well resourced, and feel that there is always someone there to listen to their problems, then the children will get a good physics education.
Physics is everywhere, and it is a really important science subject. So getting to see that, letting them see my energy and letting them see that, you know, physics is fun, and it can be fun, and it's all around you, I think that's really important. So yes, I do enjoy teaching physics now, more so than I did before.